Okay, so I'm ready to start the second part of Test 3 review. Okay, so let's look a little bit at concavity, right? So remember, when you're doing concavity, you have to follow this procedure, basically. So you want to do the second derivative to analyze concavity, and then just kind of remember it this way. If the second derivative is positive, that means you're concave up. If the second derivative is negative, then you're concave down. So we're going to start by finding the second derivative and find critical numbers, then sign chart to make this determination. Okay, so it looks like this is a product rule. So first derivative, f prime of x. The first is e to the x. The second would be the derivative of x minus 3, which is 1. Plus the second is x minus 3, times the derivative of the first. The derivative of e to the x is e to the x. So what I'm going to do is I'm going to multiply this out and simplify this before I move on to the second derivative. So this will be e to the x plus x minus 3 times e to the x. Now I'm going to go ahead and factor out that e to the x. So we do have a common factor that can pull out here. Okay, so what you'll have left is you'll have an e to the x. When you drop that out, you're going to be left with a 1 plus x minus 3. We can put together these like terms inside the parentheses. So you'll get e to the x times x minus 2. So that is your first derivative. And you want to now work on the second derivative. And this will again be a product rule. Okay, so let's move on to the second derivative. And the steps will look very much the same. First is e to the x, derivative of x minus 2 is 1, plus the second, times the derivative of the first. The derivative of e to the x is e to the x. Okay, so we get e to the x plus x minus 2 times e to the x. And then again, what I'm going to do is I'm going to take out this common factor of e to the x again. And this will go like this. I have e to the x. Once I remove that, I'll be left with a 1 plus x minus 2. I can collect those like terms, so I get e to the x times x minus 1. Okay, so that's real important. That is the second derivative. That's what we are trying to accomplish in step 1. Okay, now what we got to do is we got to find any critical numbers based on this derivative. So we've got e to the x times x minus 1. It's already in a factored form, so that makes this kind of nice. Okay, so we have two factors. The first factor we can set equal to 0, and that has no solution. Okay, you can't take a number and raise it to a power and ever get 0. It's impossible. And e is just a constant, so you're never going to take 2.72, approximately what e is, raise it to a power and get 0. It can't happen. Then we have x minus 1 equals 0, and that will leave us with x minus 1. Okay, so that is our critical value. We only have one. Step 3, we're going to go ahead and make our sign chart. Okay, so we're just looking at x equals 1. That is where the second derivative was equal to 0. Now we're going to throw some test points into that second derivative. So let's pick a number less than 1. Let's go with 0. Plug it into this second derivative that I have highlighted in blue. So that'll be e to the 0 times 0 minus 1. That's 1 times negative 1. That's a negative number, which means we are concave down. Okay, pick a test point bigger than 1. Let's keep it simple and go with 2. Plug into your second derivative. You'll have e to the second times 2 minus 1. That's e to the second times 1, which is a positive number, and that will give you where you're concave up. All right, then we just write our conclusion. Concave up is where the second derivative evaluated is positive, so that is going to be from the critical number 1 to infinity. We will be concave down where we're negative. Okay, so that is going to be from negative infinity to 1, like that. Okay, now this is a point of inflection, because the concavity did change, and this is a point on the graph, so we really just need to find what f of 1 is. Go back to the original function, plug in 1, we'll get e to the first times 1 minus 3. That's e times negative 2, so we get negative 2e. So our point of inflection is the point 1, negative 2e. Okay, so that's how that problem goes. Now what I want to do is, it's always a good idea to look at your graphing calculator to verify, and I'm going to do this as I'm going through these problems because that's something that you definitely want to learn how to do in the 21st century is, hey, check your answer. Get your calculator out, see if your calculus is doing what this graph is going to show you. Okay, so let's just do this then. I'll go ahead and let's just graph the original function. What's wrong here? There we go. Okay, so I'll graph the original function, which was e to the x, and then multiplied by parentheses x minus 3. Okay, I always look at the original function. I'll just do zoom 6, a standard window, zoom 6, kind of see what this looks like. Okay, so let's check this point of inflection. So if I trace at 1, I'm going to get negative 5.4. Now let's see if that's not the same thing as the 2e that we got. Okay, so I've got that. Now what I'm going to do is I'm just going to do the negative 2e that I got and just see if that matches that number, and it does. So what you have here is, you can see visually what's going on in this problem. You're concave down. Okay, that looks like concave down, and then this shape here is concave up. So that graph is matching what that sign chart told us. Okay? All right, so that's concavity. That's the methodology for using to analyze concavity. Okay, I'll move to the problem number 8. And this is a rational function, so we're going to do several things on this. We're going to look at asymptotes. We're going to look at the first derivative, figure out where the function increases and decreases to start with. Okay, so a vertical asymptote is always just going to occur where the denominator is equal to 0. And we're talking about the simplified form of this rational function. So on this part A, you could factor out a 4 at the top. You don't have to, but I want to just show you that nothing cancels out. So when you do a vertical asymptote, you want to cancel anything out that cancels before you figure out what makes the denominator 0. So basically what we have is x minus 4 equals 0. You can do that in your head. That vertical asymptote is x equals 4. Okay, horizontal asymptote, there's a couple of ways that we learned how to do that. One simple way is you could do this. Now, this is kind of an interesting way to do this. You could do the limit as x goes to infinity of 4x plus 12. You don't have to do it this way, but this is an infinity over infinity form. And if you did L'Hopital's rule, you would just get this. Limit x goes to infinity of 4 over 1. That's equal to 4. Now, we didn't learn it that way originally. What we learned is if the degree of the numerator is the same as the degree of the denominator, which it is, then the leading coefficient ratio is what gives you the horizontal asymptote. So see, we have the degree. There's your answer right there. 4y equals 4 over 1. So you can do that either way. Okay, so now next thing we're going to do is we need to go ahead and do our first derivative because we're going to analyze where the function increases and decreases. So when I do the first derivative, I want to take the bottom. This is a quotient rule, so bottom multiplied by derivative of top minus the top multiplied by the derivative of the bottom. And that's all over the bottom squared. We want to go ahead and get this simplified as much as we can. So this is going to give 4x minus 16 when I do a distributive property. Take the negative through, you're going to get minus 4x minus 12 all over x minus 4 to the second. So notice the 4x's go to 0. Collect your like terms, you're going to get negative 28 over x minus 4 to the second. All right, so we do have our first derivative, r prime of x is negative 28 over x minus 4 to the second. All right, now we're going to work with that derivative. Down on part D, we'll make a sign chart and analyze using test points and critical value to figure out where the function increases and decreases. Okay, so what we want to do down here is you want to go ahead and find critical numbers. So you're interested in where the first derivative is either 0 or where it's undefined. So what happens is if you take this derivative and set this equal to 0, you're not going to get a solution. Okay, if you don't see this just mentally in your head, well, you could do this if you had to. You could multiply both sides by x minus 4 to the second to get rid of the fraction. And look what happens. You get a weird thing that we call a contradiction. So that just means the derivative is never 0. So r prime of x is never going to be 0. But don't forget what you want to do also is where is it undefined? Okay, and you can do this in your head. If that first derivative is negative 28 over x minus 4 to the second, if x is 4, you have a 0 denominator. So you're going to have a critical number at x equals 4, and your function is not going to be differentiable there. Okay, so don't forget about critical numbers can either be where the derivative is 0 or where it doesn't exist. So now we just go ahead and we do our sign chart on this. Okay, the only critical number we need to consider is x equals 4. I'm going to put ND for no derivative. All right, and remember our derivative is negative 28 over x minus 4 to the second. So we're going to plug some test points into this function. Okay. All right, so let's see. Let's go ahead and take a number less than 4. Let's go with 0. Plug it into this derivative. You're going to have negative 28 over 0 minus 4 to the second. That's negative 28 over a positive number, so that's a negative number. So that will tell us the function is going to decrease. Okay, pick a test point bigger than 4. Let's go with something like a 5, I guess. Plug it in. We're going to have negative 28 over 5 minus 4 to the second. Well, that's a negative number over a positive number. So again, that's a negative. So the function is going to decrease in both of these intervals. So we're not going to increase at all. So we'll just say none is the answer to increasing. Decreasing is going to be negative infinity to 4 union 4 to infinity. And you have to have parentheses around that 4 because the function's undefined at 4. Remember, you have a vertical asymptote at 4 anyway. Okay, so we'll go ahead and just check this real quick on the calculator and see what we got here. I'm going to go way to the beginning here so I can see the original function. Okay, the original function is 4x plus 12. Notice I'm putting that in parentheses. You have to. General rule of thumb, if you graph a rational function, the numerator needs to be in parentheses and so does the denominator. It doesn't always have to be, but it's just a safe rule of thumb to put it in that way. All right, so you got to make sure it follows the correct order of operations on this. So again, I'm just going to do zoom 6. And you can see this graph is decreasing. You can't really see this part here. If I wanted to maybe zoom out on this like that, okay, now you can see a little bit better. You can see that it's decreasing everywhere. Okay, so that we know that we have a correct answer, and that's kind of a common theme as I'm going through these problems. Your graphing calculator does so much for you. All right, now when we go to the next part, we're going to find the second derivative because we're going to analyze the concavity. So the first derivative was negative 28 over x minus 4 to the second. So when we do the second derivative, you can do a quotient rule if you want to. You can also do it like this. I think I'm going to just write this like this. This is negative 28, x minus 4 to the negative 2. And then I can just use a chain rule. So if I go r prime double prime of x, I'm going to get positive 56 x minus 4 to the negative 3, and then the derivative of the inside part, x minus 4, is 1. So I get 56 over x minus 4 to the third. Okay, so that is the second derivative that we're going to be analyzing and finding critical numbers and do a sign chart on to analyze our concavity. Okay, so what happens on this one is, you want to figure out what makes the second derivative 0 or undefined. Okay, this works exactly like the increase-decrease. If you take this derivative, set it to 0, you're not going to get a solution. Okay, it's impossible to take the number 56 and divide it by something and get 0. That's impossible. The only way to get 0 out of fraction is to have 0 divided by something. Okay, so you can't do that. But we do know we're undefined. We know that we're undefined again at x equals 4. So the only critical number we would have is x equals 4, just like before. So our sign chart can be analyzed based on this second derivative. Okay, so we got a critical number at x equals 4. There's no derivative there. I'm going to plug test points in to the second derivative. That's what I have highlighted in blue up here. So you'd have 56 over 0 minus 4 to the third. The numerator's positive. The denominator's negative because you're going to have negative 64. So that's negative. That means you are concave down. Okay, pick a number bigger than 4, like say 5. You're going to have 56 over 5 minus 4 to the third. That's a positive numerator, a positive denominator. That's positive. So that means you're concave up. Okay, so we're ready to write our solution. Concave up is going to be where the second derivative was positive. So that is 4 to infinity. Concave down is going to be negative infinity to 4. Now, the point of inflection, you got to be careful about this, there is none. The reason is because you're not defined. Okay, a point of inflection has to be a point on the graph. And it's not a point on the graph. So this is kind of going back to that same thing we have here. You can see that you're concave down, and you can see that you're concave up. You can see that you're decreasing and decreasing. So that graphing, the graphing calculator is verifying that we did everything correct on that problem with the calculus. Okay, so that's a rational function. All right, I'm going to move to the next thing. I guess we're supposed to do a graph now. And we can use the graphing calculator to help a little bit on this. But the key things that we figured out on this were at x equals 4, there was a vertical asymptote. And we also looked at if y is 4, I believe we also had a horizontal asymptote. So we can go ahead and draw that like this. Now all we're going to do is just use our calculator to make a sketch of this. I'm going to put this in a, I'm going to go back and just go back to a standard window. And what'll happen on this, I'm just going to zoom, change the window, mainly the y values and the x values. I'm going to go negative 15 to 15. Scale that by 1. I'm going to do the y's the same and just see if I get a little bit better picture of it. And what you can do is just get some values. If you want to go to your table of values and get a couple of points, then you can. Okay, and that's all I usually do, just to get a little bit of accuracy, find a few good points, like here is negative 3, 0. So that's a good point. I've got a 0.0, negative 3. That's the y-intercept. I've got a 0.2 to negative 10, and so forth. So what I'm going to do on this is just kind of sketch this in. So it's going to be going down like that, approaching the asymptotes. Same thing up here. All we're interested in is just kind of a rough sketch of how that graph goes. Okay, all right. So next thing we're going to look at is an optimization problem. Okay, now when you're doing optimization problems, it's always kind of important to, identify the variables that are in the problem. Okay, you've already got a picture here. It's always kind of good to draw a picture unless you're given a picture like on this one. Then typically what you do is you see if there is an objective equation that somehow relates the variables. The third thing is you want to get an objective function, and that has to be in one variable. And the objective function is what you're going to be working with the derivative on and finding critical numbers and so forth. Okay, so once you get down to that point, you do the, first derivative, you find critical numbers, you do a sign chart. If it's necessary to do a sign chart, you can do that to verify if something's a max or a min. You could even do the second derivative test if you wanted to. So when we read this problem, it says that park ranger has 600 feet of fencing material used to construct a rectangular three-sided fence bordered on one side by a river, shown in the figure below. Okay, so you have three dimensions. You have y, and then you have x. So we've identified our variables. When we do the objective equation, well, what's that going to do? That's going to just be saying, let's find the perimeter. Well, the perimeter would be found by adding these three sides up, and we know that that adds up to 600. So see, that's your objective equation right there. Now, if you read on, it says find the dimensions of the fenced region that maximize the area. So since that's area, that is going to be your objective function, is going to be an area function. All right, so we're going to start off, I'm just going to call this a of xy. It's going to start off with two variables. If I find the area of this figure, it's base times height. That's a rectangle, so that's just x times y. But what we need to do is get this down to one variable. So take your objective equation in one, and you can solve it for either variable. It doesn't make any difference. It's just as easy on this to solve this one for x. Okay, so what I'm going to do is I'm going to take x, and I'm going to replace it with 600 minus 2y. So now I've got an objective function, and it's going to have one variable y in it now. The x is going to change to 600 minus 2y. I got the y alone. Okay, so we've got our objective function, and we're all set. Once you get that objective function, now you're going to do derivative, first derivative, critical numbers, sign chart, second derivative test if you want to verify whether you get a max or min. So I'm going to go ahead, when I move on to step 3, I think what I'll do is I'll go ahead to start with, I'll just distribute. So I get 600y minus 2y the second. So I'll go ahead and do my first derivative. That's going to be 600 minus 4y. I want to set that equal to 0. Okay, I'm going to add 4y to both sides, so I get 4y equals 600. And then y is just going to be 600 over 4. So that will give you your critical number then. So that is 150. Okay, so we got our critical number right there. We got our critical number. So now what we need to do is kind of see, is this a max or a min? There's a couple of ways to do this. If you wanted to go ahead and do like a sign chart, then it would go like this. Okay, this is a good way to verify if this is a maximum. So you have y equals 150. Now your first derivative is this thing right here. That's what you're going to plug your test points into. So if you took a number a little bit below that, like say 100, and just say 100 or something, if you do 600 minus 4 times 100, that gives you a positive number. That means the function increases. If you take a number bigger than 150, like say 200, plug it in, you get 600 minus 4 times 200. That gives a negative. That means the function's decreasing. So what it means is this graph is going up, hits a high point, goes down. So that right there verifies that that 150 is a max. Okay, that's one way to do that. The other way to do this is, in the world of technology, is to graph your function. Okay, so graph the function that you had in terms of one variable. That's what you want to graph right there. So let's put in 600, and it doesn't matter that we just use x instead of y. And we got minus 2x squared. We got 150 as a max, so that'll kind of help us with our window. X is a dimension, so the smallest dimension possible would be 0. Okay, but we want to go up bigger than 150. Why don't we just double it and go to 300, scale that by 100. Okay, now that leaves you with your y, and your y is representing area. So you're not going to have negative area, so start that at 0. And another thing you can do is just look at your table and just kind of judge how big these numbers are getting. They're getting pretty big. So maybe we'll start with 50,000 or something like that. Okay, so I'm just going to start maybe 50,000, scale by 10,000, and I want to see what this thing looks like. Okay, that was a good guess. Okay, so what we get then on this is if we were to trace at 150, you can pretty well tell that's a max right there. So visually, you're okay with that. And the other thing, when you do this, is this thing right here is the area. Okay, so what you end up getting on this is you're going to get, we know what y is. So to finish up this problem, we have y is 150. We verified it's a max. Now x is equal to 600 minus 2y. That comes from that objective equation. So we get 600 minus 2 times 150. We, of course, know what y is. So that's 600 minus 300. So that's equal to 300. So our dimensions, and it's good to write your dimensions on here, x is going to be 300 feet, and y is going to be 150 feet. Okay, and the area, if you wanted to find the area, you just do base times height. So notice what would happen if you did 300 times 150. Well, you would get this 45,000. Okay, so I'll just kind of verify that for you, and then we're all done with the problem. So the graphing calculator really comes in handy as a nice means for verifying what your calculator is finding anyway. So if you were asked to find the area, that would be 45,000, and of course the units would be square feet. Okay, so there's our dimensions. That's the area that will make a maximum garden or rectangular, whatever this was, rectangular plot of land that will maximize the area. It makes the area as big as possible. Okay, so that's a typical type of optimization problem. Okay, now I will move to the next thing here, and I had a couple of something. There we go. All right. Okay, so on the next thing, we're going to look at some L'Hopital's rule type problems here. Okay, something got kind of messed up here when I did this. I don't know what that is. Let me get rid of that. There you go. All right. Okay, so next thing we're going to look at is some L'Hopital's rule problems. And there's several different forms that we learned about. The first thing I'm going to start with is just kind of reminding you some of the different forms. One of the forms, the typical ones are infinity over infinity and then 0 over 0. And there was a lot of other ones too. There was ones with exponents in it as well. We'll kind of look at those as we get to those. So we're going to start with these two forms right here. So to begin with, what you always want to do is see what the form is. And, you know, a lot of times you can just do this in your head. So if you replace x with an infinitely big number, you're going to get an infinitely big numerator and an infinitely big denominator. Okay, so you want to know that, okay, that's an infinity over infinity form. So that means that we can do L'Hopital's rule to evaluate this limit. So when we do this, I usually like to write an equal sign and LH. That's just the way I like to notate that I'm doing L'Hopital's rule. Okay, the derivative of the numerator is 2e to the x. The derivative of the denominator is 2x. Now, you could go ahead and you can cancel out the 2's. You might as well do that. I mean, you don't have to, but you're going to be left with the limit x goes to infinity of e to the x over x. Okay, so what I have is I still have an infinity over infinity form. If you replace, if you have e to the infinity over infinity, it's still that form, so you can do L'Hopital's rule a second time. So I'm going to put LH2. Okay, so if I do the derivative of the numerator, again, I get e to the x. If I do the derivative of the denominator, I get 1. Then if I just plug this in now, look what happens. I don't have an indeterminate form anymore. I just have an infinitely big number. So the answer to that problem is infinity, right? And that's how L'Hopital's rule would be used to handle that. Okay, all of these problems, too, pretty much on L'Hopital's rule, you can visually tell if you're on the right track with these things. So what I'm going to do is I'm going to graph the original function, which is 2e to the x, and divide that by x squared. And what I want to do is I'm just going to, just standard window, I'm going to go zoom 6. Okay, it looks like that graph's swinging up, kind of going like this. And yeah, what's going to happen on this is it looks like if our answer is infinity, that just means that thing is going to go to infinity. And another way to look at this is look at your table of values. Just look what happens on this problem. Okay, as you get bigger and bigger, as x gets bigger and bigger, look, we're in scientific notation already when x is 32. I mean, it gets to be huge numbers. And the reason that I like to think of on this problem is what happens is e to the x and x squared, this outpaces squaring. Okay, I mean, it outpaces it by a long shot because this is really like 2.7. And when that gets to a bigger number, I mean, the exponent gets infinitely big, that outpaces the x squared. And that's why it ends up going to infinity. Okay, all right, so that's L'Hopital's rule on that one. All right, next problem. Well, again, start the same way. Evaluate at 1, we'll have sine of pi times 1 over 1 minus 1. So you're going to have sine of pi over 0. On a unit circle, remember, pi is halfway around the circle, goes to the point -1, 0. Sine is the y value, so you would get 0 over 0. So this is a 0 over 0 indeterminate form. So that means, yes, we can use L'Hopital's rule to evaluate this limit. Okay, but do the form. It's super important. Don't just jump into doing L'Hopital. Make sure it's the right form. If it's the right form, then you can do L'Hopital. If it isn't, you can't. Okay, so we're going to go ahead and L'Hopital this sucker. So the derivative of the numerator is the derivative of a sine is a cosine. This is a chain rule. So the derivative of pi x is going to be pi. Okay, you got the basic rule, derivative of sine x is cosine x, but this is the sine of a function, so you're applying the chain rule. Okay, the denominator is easy. The derivative of x minus 1 is 1. Okay, so let's see what we got here. We have the limit as x goes to 1 of pi cosine pi x. All right, now what I'm going to do on this is I'm just going to plug the 1 in and calculate and see what happens. So I got pi cosine pi times 1. So that is equal to pi times the cosine of pi. Well, if you look at the unit circle, the cosine is the x value. So you would get pi times -1. So you get negative pi. Okay, so the answer to that problem appears to be negative pi. And let's take a look at this on the graphing calculator to make sure. Okay, so if you're doing a trig function, I think it's pretty important to make sure that you're in Radian mode. So you press your mode button, we're in Radian mode. The original function has to be put in like this. Numerator is sine pi x. Okay, divide by, make sure you put this in parentheses, and that will be x minus 1. Okay, now you could do this in a standard window if you want to. It's a trig function, so if you just graph it in a standard window, it's you're not going to see it very good. So I'll probably just go through. We're interested in the limit around x equals 1. So why don't we just go 0 to 2? That's all we care about is what's going on when x is 1, a two-sided limit. And let's do kind of some small numbers like -2 to 2 and just try this like this. Okay, all right, maybe make the y a little bit smaller. Let's make that y go to -4. Whoops, hold on. Let's go, let's go -4 to 4 like that. Okay, so there's my graph. Now you're going to see on here, see that little hole? You can actually see this. There's a little hole there. This function is undefined at x equals 1. So what happens on this problem is if we traced it a number real close to 1, and it's a two-sided limit, so if we did 1.001, we're getting pretty close to pi, negative pi. If you traced it 0.99999, okay, you're pretty close to pi. So see, that graphing calculator is verifying what's going on this problem. So that's really cool. All right, so it is indeed negative pi. Who would have thunk? All right, so that's kind of how that goes. And this graph, again, is just got a little bubble in there, and it is approaching negative pi. So that's right. Okay, so those are two pretty straightforward L'Hopital's rule problem. The next one gets into a form with an exponent in it. So there's a lot of different types of problems that we learned how to do. Down here, what happens is if you go ahead and plug 0 in, this is a right-hand limit around 0. If you plug it in, you would get 1 plus 0 to the cotangent of 0 power. So that would be 1. Now, the cotangent of 0, if you want to look at this, just look at a unit circle. 0 radians means you're on the x-axis at the point 1, 0. A cotangent is x over y. So that means you would have 1 over 0. So you're undefined. The cotangent of 0 is undefined. So what happens is this, is that that's going to go to infinity. So if you think about just taking like 1 divided by a number real close to 0, okay, all I was going to do is give you a humongous number. It's going to get bigger and bigger and bigger. So you have a vertical asymptote on that on a cotangent of 0. If you look at the cotangent graph and remind yourself of that, you have a vertical asymptote. So you have a 1 to the infinity form. That's one of the type of forms that we learned about, see. Okay, so the way that I taught you all how to do this is if you have an indeterminate form that has an exponent in it, then it's to your advantage to change this into logarithms. So what I like to do is just pick a variable and set that equal to the limit that we're analyzing. Okay, so I'm going to go ahead and do this, and then I'm going to do the natural logarithm of both sides. Okay, and you can go within the limit and do this, the logarithm of the function. Okay, so we got x is approaching 0 from the right-hand side. We have ln 1 plus x to the cotangent x power. And the whole purpose of this is we can bring that cotangent down in front. So we're going to have this thing, basically. Let me zoom on this a little bit. You're going to have ln p is equal to limit x goes to 0 from the right-hand side of the cotangent of x times the natural logarithm of 1 plus x. Okay, so it's advantageous to use logarithms because you can ultimately write this thing. What you're always trying to do with these different forms is you're always trying to ultimately get these things down, if you can, to infinity over infinity or 0 over 0. So what I'm going to do on this one, it's advantageous to have a fraction here. So if I have a cotangent, you learn in trig, of course, that the cotangent of x is 1 over tangent x. So let's try to approach it this way. Okay, keep bringing the ln p down, because if you don't, you're going to forget about it. And you're going to get the wrong answer. So let's write this as the limit as x goes to 0 from the right-hand side. Let's write this as ln 1 plus x over a tangent of x. And let's see what our form is on this problem. Okay, so what's going to happen if you plug a 0 in, you're going to have ln of 1 plus 0, and you're going to have tangent of 0. Well, you're going to get ln of 1, tangent of 0 is 0, ln of 1 is 0. So you get a 0 over 0 form. Okay, now if you're using a calculator, I mean, I don't want a student to have to grab their calculator to do this, but hey, your calculator will bail you out. If you do ln of 1, you got 0. And if you do tangent of 0, you're going to get 0 also. So don't forget you have that at your disposal to use. So that does mean that we can use L'Hopital's rule. Now bring the LNP down and don't do the derivative of LNP. We're doing L'Hopital's rule. So what we're going to do is we're going to do the derivative of the numerator. And the derivative of a natural log, remember, is 1 over the function. Now, this has got a function, a chain rule. The derivative of the inside part, 1 plus x is 1. Okay, the derivative of a tangent is a secant squared x like that. Okay, so we're going to probably clean this up a little bit, just doing some algebra and kind of see what we get. Okay, what we have is 1 over 1 plus x, and what we're doing is we're really dividing by a secant squared x. There's a lot of ways to approach this. You could change that to a cosine if you wanted to. So you have a lot of options. If you want to, you could say that this is really divided by 1 over cosine squared x. I think it's always wise to work with cosines and sines and tangents if you can. So what you really have, when you algebraically simplify this, is 1 over 1 plus x times cosine squared x over 1. Okay, and stuff like that is kind of good. Just do that on scratch paper, and we'll bring this down. So we have LNP equals the limit. X goes to 0 from the right, and what we have is we have cosine squared x over 1 plus x. Okay, and let's just plug it in now, and let's see what we get. Okay, so we're going to get LNP equals, and we're going to have cosine of 0 squared, and then we're going to have 1 plus 0. So we don't have a 0 over 0 form anymore, and what we get is the cosine of 0 is 1, so we get 1 squared over 1, so we get 1. Now, that's not the answer. That's the reason why, when you're doing these problems, that you want to keep this ln down. So we have LNP equals 1, and remember, that's a base e, so we'd have e to the 1 equals p. So the answer to that problem is going to be e. Okay, who would have thought? But that's the way that works out. Okay, and the thing on that is you have to know when you're using logarithms. And why you're using logarithms. And ultimately, the whole key to doing this problem was getting this thing into this form. You had a 0 over 0 form limit right here, and then you could go through L'Hopital's rule. All right, so let's go ahead and let's check this one also, because it's kind of an interesting answer, and let's see what happens on this. So if I do this, the problem we just did was parentheses 1 plus x raised to the cotangent of x power. Well, the way you have to put this in is you got to go 1 divided by tangent of x. Okay, I mean, that's one way to put it in. The cotangent's 1 over tangent x. Okay, and what we'll do on this, we're interested in the limit as x goes to 0. So for the window, let's just make sure that we're a little to the left of 0 and a little bit to the right of 0. Like that. Let's just try this window here and see what this thing looks like. Okay, so what did we do? We're looking at a right-hand limit as x goes to 0. So if I trace it a number just a little bit to the right, something like that, look what happens. That's e. We're at 2.718. That's a decimal approximation for e. So it just took hardly no time just to graph that and verify that that's the right answer. That is so cool. Couldn't do that back when I was in college. Back in the days when we didn't even hardly have calculators and stuff. So I just think graphing calculators make students understand concepts visually so much better back in the day when I was a student. Take advantage of it. Okay, so let's see. We'll look at a few more L'Hopital's rule problems here as we're going through this. That one is a good one, to study and practice on. Students sometimes have a hard time with that one. Okay, let's see what we got going on this problem down here. Okay, I was going to work on that last one, got a little sloppy. Sorry about that. Okay, well, let's see what form we have on this. Now what's going to happen on this is if you replace everything with infinity, you're going to have infinity squared times the sine of 1 over 4 times infinity to the second. So for all practical purposes, that's infinity. And this is really sine of 0. Anytime you have 1 over a really big number, that just is getting close to 0. And the sine of 0 is 0, so the original form that we have is infinity times 0. Okay, that's one of the indeterminate forms that we learned. I recommend that you review all those terms. Okay, so remember, the whole key to doing L'Hopital's rule, for the most part, is always try to get these things into one of these forms. Infinity over infinity or 0 over 0. So we want this to be a fraction. Right now it's not really a fraction. We got the sign of a fraction. But there's a couple of ways we could do this. We could bring that sign down to the bottom and change it into a cosecant if we wanted to. We could also move the x down to the bottom like that. And that's what I'm going to do because I like to have a sine more than I like a cosecant because I'd rather do a derivative of a sine than a cosecant. You know, that's just my thought anyway. So let's write this like this as the limit as x goes to infinity of sine but let's go ahead and just write that as 1/4 x to the negative 2. We're probably going to have to do the derivative of that anyway. And then, hey, if you bring the x to the second down, it's just going to give it a negative exponent. Okay, like that. And let's see what kind of form that we have now. So if we were to go through and plug in right now infinity, see what we really have is we really have the sine of 1 over 4 times infinity squared. And then x to the negative 2 is really 1 over x to the second. So what happens is you get sine of 0 over 0. Right now you have a 0 over 0 form, okay, because you're doing the sine of 0. And remember, again, this thing right here is real important. Any number divided by infinity, doesn't matter how big that numerator is, you know, it can't compete with infinity. So that's going to go to 0. So we have a 0 over 0 limit right now. So that means we can move on and do L'Hopital's rule. Now I'm going to erase some of this mess from that last problem. I kind of want to get this a little bit cleaner as I finish up this problem. You can always rewind videos and kind of look at what I did, you know, and pause and think about what's going on in the problems if you need to, okay? All right, so we're going to do L'Hopital's rule. And it looks like we're just going to start by doing the derivative of the sine. The derivative of sine is a cosine. Then we've got to do a chain rule, so we have to do the derivative of what's inside. So that would be 1/4 times negative 2x to the negative 3, like that. The derivative of the bottom by power rule would be negative 2x to the negative 3. Now what I like about this problem is look at this. Those things cancel out. That's in the numerator. That's in the denominator. Those things cancel out. So let's kind of work with what we're left with here. We have the limit, x goes to infinity. Now, we have a 1/4. I could bring that in front of the cosine if I wanted to. So I have cosine of 1 over 4x squared. Then I've got this negative 2. So the idea now is you just need to simplify this. Now, you know, when you're thinking about how this arithmetic goes, you have 1/4 and you're dividing by negative 2. So that is 1/4 times 1 over negative 2. So really that's negative 1/8. So you're going to have the limit, x goes to infinity. You can just write down that negative 1/8. You can even pull that out of the limit if you want to. So we're ready to plug in and see what happens. Okay, so see, just work out your arithmetic methodically on scratch paper if you need to. Okay, and now let's see what happens. So we have negative 1/8. We're going to have cosine of 1 over some infinitely big number. So this is negative 1/8 cosine of 0, and the cosine of 0 is 1. So we get an answer of negative 1/8. Okay, so that's the idea. You have to get the derivative. You have to work out all the algebraic details on that. That would be the solution to that problem by L'Hopital's rule. Okay, infinity times 0 form You need to move something down to the denominator. I thought it was a lot easier to just move the x squared down, so it becomes x to the negative 2. Verify that it's a 0 over 0 form, then do the derivative. And then from there, it's a little bit of algebra, some arithmetic. They're going to get negative 1/8. All right, so I'll go ahead and put this one in the calculator also and just kind of continue to do this. We do these problems. We have x squared, and then we have sine of 1 over, and you have to be careful how you put this in. You got to put 1 over parentheses for x to the second. I see students do that wrong a lot of times. And we're interested in how this graph behaves at infinity. So let's just do zoom 6. It looks like it's kind of leveling off at something. Let's just, let's go down and let's look at the table of values. So it looks like it's just going to 0.25. Now we didn't get that. We got negative 1/8. This possibility, I got a wrong answer. I made a mistake in here somewhere. And it's okay that you see that. Two things I want to check. I want to make sure I'm graphing the right thing, and I definitely am. So it looks like maybe 1/4 is the answer to this problem. So let me go through and let's look at this. Some of you may have already caught something I did wrong possibly. So let's go through. Let me pause here, see what I did wrong, and then I'll come back and fix it. Yeah, I already see where I messed up. Okay, and I apologize for that. Sometimes if you're not real careful, you kind of get in a hurry. Things like arithmetic, you're just going to mess up. Hey, look what I did here. This is really stupid. Okay, the x to the negative 3's cross out, but so do the 2's. Okay, I didn't even see that. So see what I'm left with is I've got a 1/4. Now I got that negative left over there too. So I have a negative 1/4 cosine of 1/4 x to the negative 2 after that cancellation. Okay, like that then. And let's see from here. Okay, all right, now I made 2 mistakes in here. All right, I'm going to just go here. Okay, and show you what I did. I just did a couple of really stupid things here. All right, so it goes like this. We're ready to do L'Hopital's rule. This time I'm going to take my time, be a little bit more careful with it. So the derivative of a sine is a cosine of that argument times the derivative of what's inside. So 1/4 is a constant, but that's negative 2x to the negative 3. I don't know why I did that. Okay, go down the bottom. The derivative of x to the negative 2 is negative 2x to the negative 3. Well, I made this problem way too difficult. That and that crosses out. Okay, so what we're left with is the limit as x goes to infinity of 1/4 cosine, and I'm going to write that as 1 over 4x to the second. Okay, so here's what happens. When that goes to infinity, you get 1/4 cosine of 1 over infinity, and of course 1 over infinity is going to 0, so you get 1/4 cosine 0. Cosine of 0 is 1, so that's how you get that 1/4 of that 0.25. So again, I could lie to you and said I did that on purpose, and I wanted to teach you that your calculator can bail you out of situations. I didn't mean that, but anyway, the calculator, that's another good thing. Okay, it can help you find problems and stuff like that. So 0.25 or 1/4 is the answer. Okay, all right, I apologize for that. Okay, all right, let's see, one more L'Hopital's rule problem. And on this, the next thing that we're going to look at is one more L'Hopital's rule problem. Let's plug in the 0. So we have 0 times cosecant of 0. Now, on a unit circle, 0 radians is the 0.10. Okay, so what happens on this then is we get this. Remember, the cosecant is r over y. In a unit circle, r is 1, y is 0. So you're undefined. Now, if you're undefined on a trig function, it means there's a vertical asymptote. which ultimately what that's going to mean is that we have, we're going to infinity. So this is a 0 times infinity indeterminate form. Okay, so we know that we got a valid form. Okay, so again, we need to turn this into a fraction. And we need to see if we can just make this into either an infinity over infinity or 0 over 0 form. You have two choices. You could bring the x to the bottom. You could bring the cosecant to the bottom. My thought on this, it would be, let's bring that cosecant down because we know that a cosecant of x is 1 over sine x. I would rather have a sine than a cosecant. So I'm going to go ahead and write this as the limit as x goes to 0 of x over sine x. This is going to be a super easy problem. Plug a 0 in, you get 0 over sine 0. You have a 0 over 0 form now. Now, the original form is 0 times infinity. That's what I'm asking you to put down. But you got to translate this into a fraction. Okay, now you're ready to L'Hopital the sucker. All right, so what do we do? Derivative of top bottom, this will be a real simple problem. Derivative of x is 1. Derivative of sine is cosine of x. Plug in the 0, you get 1 over cosine of 0. And again, we know cosine of 0 is 1. So we get 1 as the answer to the problem. Okay, so if you were putting this in your graphing calculator, now you would pretty well have to put this in this form like this. Okay, what you're doing is you're doing x over sine of x like that, and we're looking at the limit as x goes to 0. So, I got just kind of a standard window in here. That's kind of a neat looking graph. Well, okay, well, let's pick a number real close to 0 and trace it out. So 0.0001, look at that, that gives me 1. Okay, so what happens there is you are getting close to 1 on both sides. Okay, so right there, that graph right there, very simply, easily verifies that we have the right answer on that problem. Okay, all right, I wanted to spend a lot of time with calculator because it helps you make so much better sense out of these problems. If you just do it mechanically and don't ever think about what the graph looks like, then, it's okay if you have confidence in your calculus and algebra skills, but it sure is nice that you can verify stuff. All right, so let's see, a couple of more things. Next thing we want to transition to is antiderivatives, and a lot of what we're going to do in here is just lots of antiderivative rules and everything. So what I'm going to do here is just kind of give a summary of some basic antiderivative rules. The more you know, the better off. So, of course, we have like the power rule for an integral. That we add 1 to the exponent, you divide by the result, and you add c to it. That's going to pop up in this first problem, right? The other thing is if you have a variable just of a constant, that's going to be kx plus c. Okay, because remember, the derivative of kx is just k. So that's going to pop up in this problem. So I'm going to go ahead and do this problem 9a because we're simply applying this rule. The other thing that we learned is like if we have, say that you have a constant times a function, then you can pull that out. So that's a times integral f of x dx. Another thing we learned is if you have two functions added or subtracted, and that can be more than two functions, then you can split this up into two integrals. Okay, so all of these rules right here that we learned, they all come from properties of limits. And you kind of remember your properties of limits. Well, integrals work pretty much the same way based on that. So I'm going to split this up. I've got 3 different functions, so I can split it up into 3 integrals. And you can do this problem, a lot of it in your head. I'm just going to take a couple extra steps on here. So I'm going to write this as 2x to the 4th dx minus the integral. Let's go ahead and change that to x to the 2/3 dx. And then the next one would be just the integral of pi to the 10th dx like that. Now you could also move that 2 out like that. So now we're ready really to just do the integral like this. So 2 is a constant. That'll come out of the integral. Just write it down. Add 1 to the exponent. That's x to the 5th over 5. Do the same thing here. Add 1 to the exponent. You're doing 2/3 plus 1. So that's 5/3. So that's going to be 5/3, and you're going to divide by that result. Okay, this is a constant. You're not going to say pi to the 11 over 11. No, because pi is not a variable. That's a constant. So that is pi to the 10th x, and then plus c. So then all we got to do is just kind of clean this up. We're going to have to write our answer as 2/5 x to the 5th. Okay, you're dividing by 5/3. Dividing by 5/3 is the same as multiplying by the reciprocal. All right, so that would be your antiderivative right there. Okay, so those rules apply to a lot of the integrals you're going to do. Power rule, constant rule, breaking up into 2 or more integrals, and so forth. Okay, now there is something you can do on this also. You can tell you're right. If you do the derivative of your answer to check, look what happens. Okay, you just would have 2/5 times 5x to the 4th minus 3/5 times 5/3 x to the, and you'd subtract 3/3, so that'd be 2/3, plus pi to the 10th plus 0. Okay, look at this. 5's cancel out, so you have 2x to the 4th. That stuff cancels out. You have x to the 2/3. See, it's back to the beginning. So it's not hard typically to just take the derivative of your answer and see if you're right. Okay? All right, now let's go ahead and kind of get this one set up on this next one here. Now, I see 3 functions. So I can break this up into 3 integrals. And you're going to have an integral of 1/3 cosine x dx minus the integral of e to the 3x dx plus the integral of secant x tangent x dx. Okay, and again, you can bring that third out. I'm just going to kind of bring this out. You can do this in your head. I'm just going to bring out the 1/3, and I've got this now. Okay, so what are the rules that we have to know on this problem? Okay, the rules is we have the integral of the cosine x dx is equal to sine x. Okay, and we know that because the derivative of the sine x is cosine x. We also have the rule, the integral of e to the ax dx is 1 over a e to the ax plus c. And then the other one we have is secant x tangent. Well, just think about what function did you learn to take a derivative of that gives secant tangent? Okay, well, that was secant x. Okay, so these are the 3 rules that we have. So what we're going to have is 1/3. The antiderivative of cosine is sine x. Just do it backwards. Derivative of sine is cosine, so you know you're right. 1 over 3 e to the 3x would be what that is. That's using this rule for exponentials, plus the antiderivative of secant tangent is secant x plus c. Okay, so that's your answer right there. You can take the derivative of that. You can almost do that in your head. Okay, and take the derivative of it, and you will get back to where you started. Okay, so that's how that goes. Okay, let's go to the next and see what we got here. Again, we have 3 functions, so we can split this up into 3 integrals. I'm going to write this as the integral of 1 over 1 plus x squared dx plus the integral of 1 over square root of 1 minus x squared dx, and then plus the integral of 2 dx. Okay, well, what integral rules did we learn? Well, here's a couple of more. Again, it's not new rules. If you remember your derivative rules, then you're really just thinking backwards. So the integral of 1 over 1 plus x squared dx is the inverse tangent, okay, because we learned that the derivative of inverse tangent is 1 over 1 plus x. The integral of 1 over square root of 1 minus x squared dx is inverse sine. And then this one, of course, we learned that the integral of a constant, you just tack on the x. So the answer to this problem is you got no rules. This would be inverse tangent plus inverse sine plus 2x plus c. Right, so that's a matter of knowing your basic derivative rules and your basic integral rules. Okay, the antiderivatives you're doing here are very basic, just applying rules. Okay, all right, let's move on and kind of get this wrapped up here. So I got a couple more things that I want to go through on some integrals to get this wrapped up. Okay, now this one is an initial value. So the first thing you're doing on this is I've given you the derivative. You're finding the function. So the way you find the function, if you know the derivative, is you find the antiderivative. So you do the integral of 3x plus sine pi x dx. Okay? Now, you can do this in your head. You can also split this up like this. You could write this as 3 times integral of x dx if you want to, plus the integral of sine pi x dx. Okay, or you can just do this in your head. The only real thing I'm doing here is a power rule, but also we have this rule. The antiderivative of sine ax dx is 1 over a, and the antiderivative of a sine is a negative cosine ax. Okay, and see, double check this. If you do the derivative of a negative cosine, look what happens. Of ax, you would get negative sine ax times a. And the reason you have that 1 over a, because that'll cancel out, and then you're back to sine of ax. Okay, when you learn these formulas, you've got to do derivatives to kind of help you understand why these rules work the way they do. So there's a rule we learned. The integral of sine ax is 1 over a times negative cosine ax plus c. So what we're going to have is 3x to the second over 2, that's a power rule, plus 1 over pi times negative cosine pi x plus c. So let's clean that up. We have f of x equals 3 halves x to the second minus 1 over pi cosine of pi x plus c. All right, so that's your antiderivative. Step 2 is find c. We have an initial condition. So if you have f of 2 equals 3, then it just really means this, that the 3 is what f of x is. X is 2. So what you can do is you can plug in a 2 for x, and then f of 2 is going to be 3. So you can solve this equation. So you'll have 3 equals 3 halves times 2 to the second minus 1 over pi cosine of pi times 2 plus c. So this is 3 equals 3 halves times 4 minus 1 over pi cosine of 2 pi plus c. Okay, this would be 3, this is 6, 4 over 2 is 2, and then the cosine of 2 pi is 1, because again on a unit circle, 2 pi means 1 lap around the circle. Okay, cosine's the x value, so that's 1. So we're going to now just solve this for c. So we'll do 3 minus 6 plus 1 over pi equals c. I'm just subtracting 6, adding 1 over pi to both sides. So our answer to our problem then is going to be this. We're going to get f of x equals the antiderivative, 3 halves x to the second minus 1 over pi cosine pi x plus c. But c is negative 3 plus 1 over pi. So that's it. That's how you put that together. That's called an initial value problem. It actually gives you a specific solution to a basic differential equation. I've really given you an equation with a derivative in it. So that is a simple differential equation. All right, so we find a specific solution. Okay, all right, two-step process. Find the antiderivative, find C, using the initial condition. Keep it simple. Okay, next thing is looking at areas of definite integrals. And we learned quite a few properties of definite integrals on here. So what happens on this one, we're doing the integral a to b of f of x. Okay, from a to b, the area is above, so it's positive 12. That's the answer to that definite integral. We're looking at an area. The next one is b to c. So from b to c, we are below the x-axis, so the answer to that definite integral would not be 10, it would be negative 10. So you have to pay attention to if a region's above the x-axis versus when it's below. Okay, now if you go to a to c, well, we have to break this up into two integrals. So you learned this property. We can break this up like this. We can split this up, so we're going to end up getting the integral a to b f of x dx plus the integral b to c f of x dx. Okay, now see, we got the integral a to b was 12. We got the integral from b to c was negative 10, so this net area would be 2. You can really do that problem in your head. Certainly, it's easy to do in your head, but that's what you're learning is the property of integrals. Okay, the next one, you're going from b to d. It'd be negative 10 plus 8, but more specifically, you break this in, you go b to c, f of x dx, plus, then you go c to d, f of x dx. Okay, so the integral from b to c is negative 10. The integral from c to d is above, so that's 8. Negative 10 plus 8 is negative 2. So that is your net area. That's the answer to that definite integral. Okay, basic arithmetic, but you have to understand the properties of integrals, the difference between a region being above the x-axis and below the x-axis. That's the main thing. Okay, a couple more things, one more problem, then we'll wrap up this part of the review. A little bit more of the same stuff. This time I'm giving you 3 integrals, giving you the value of 3 specific integrals. So again, this is really testing, does a student know their properties of definite? So this first rule is we reviewed that you can bring a constant out. If you have a constant 3 multiplied by a function, it can come out. So you have 3 times the integral 0 to 3 times f of x dx. Okay, did I give you the integral? Yeah, I did. I gave you the integral f of x dx was 2. So what we get here is we just do 3 times 2, so we get 6. Okay, that one's pretty straightforward. Okay, the next one, you can do kind of the same thing. You can bring out the negative 2. So let's write this as negative 2 times the integral 3 to 6 of g of x dx. So we got to see, did I give you the integral 3 to 6 g of x dx? Yeah, I did. I gave that right here. I gave that as 1. So that matched up. Whoop, I'm doing the wrong thing. I wonder if okay, all right, I see what I did. Okay, so I'm wondering on here what my mistake was. I am suspecting that this was intended to be g of x dx. Okay, I mean, I obviously that's what I meant. All right, so let's change that to g of x. All right, so to finish this problem, we'd have negative 2 times 1, okay, because that matches up. Integral 3 to 6 g of x dx is 1, so the answer of that problem would be negative 2. Okay, now the next two, a little bit more advanced. Okay, we have 2 functions. We can break it up into 2 integrals. The constants can come out of the integral, so you can do this in one step if you want to. You could just say 2 times the integral, 3 to 6, of f of x dx, plus 3 times the integral of g of x dx, like that. And then let's just see if we were given these 2 things then. Okay, so f of x 3 to 6, that was given. That right there was given as negative 5. So we're going to have 2 times negative 5 there. And let's see, were we given the g of x? Yeah, that was 1. Okay, so we're going to have 3 times 1, so that would be negative 10 plus 3, so that is negative 7. Okay, so that's how that goes. All right, now next one we have the limits backwards. We learned this property that if you have the integral a to b of f of x dx, if you change the limits, then you get the opposite answer. Okay, that's a basic property that you have to know in order to do this problem. So you start off by writing this as negative the integral 3 to 6 for f of x minus g of x, and then you got dx. So we can split it up into 2 integrals. Be careful because that negative, you need to have like a big bracket. So we're going to say 4 times integral 3 to 6 f of x dx minus the integral 3 to 6 of g of x dx. Like that. So let's see what we have then. Okay, whoops. Okay, so I've got the negative here. 4 times the integral f of x dx was given as negative 5. The integral g of x dx was given as 1. So we work this out. We'd have negative 20 minus 1. So that is negative 21. So that answer is 21. All right, that's how that goes. That one's got one extra little twist in it. So again, we just developed the idea of a definite integral. So mainly what we're looking at in this exam is properties of integrals. Okay, well, that'll wrap us up. Hopefully this will help. If there's any area of this that you need to go back and review, then please do so. Okay, otherwise, happy studying.